Well, good morning, pre-calculus students. And we are ready to go with our next section here, which is 9.3, the one that I tried to start yesterday. We're actually ready to start it today. And so we are going to be looking at sequences. So as you've kind of figured out, chapter 9 is definitely a different kind of mathematics. It's what we call discrete mathematics, where the systems aren't continuous. They kind of have those gaps as things are either yes or no. It's whole numbers. You're not getting partial numbers in between. So let's go ahead and let's look at sequences. We're going to see if it still falls into this discrete category. So what is a sequence? Well, mathematical sequence is similar to what we think of when we think of the term just sequence in general, when we refer to that. And it's essentially an ordered list of numbers. The key thing here is the ordered. If it's just a list of numbers and the order doesn't matter, it's another mathematical thing that we talk about called a set. That would be where the order is not significant. But once we place them in order, and they definitely have a particular order, we have a sequence. All right, so we have different kinds of sequences. The first is finite. That's where we have a limited number of terms. So for instance, I could give you a sequence like 2, 4, 6, 8. Okay? That's a 4-term sequence. Starts with 2, ends with 8, goes up by 2 each time. That would be it's ordered from least to greatest. That would be an example of a finite sequence, limited number of terms. In contrast, there's also an infinite. So for instance, if I was to designate to you the natural numbers, okay, that would be a sequence, starts with 1 and goes up and continues infinitely. So there's an infinite number of terms in that. But once again, we see it's got a distinct order to it, and so it meets the definition of sequence. All right, let's talk about how we're going to define a sequence. So for instance, if I want to talk about the natural numbers, I don't want to always say the natural numbers. Or I certainly don't want to start talking about it if I've got an unusual pattern going in. For instance, I say the natural numbers starting with 5. I don't want to start, there's too much verbiage. We want a very concise mathematical way to symbolically denote a sequence. So here's what we're going to do when we go to define a sequence. One way to define it is what we call an explicit definition. Explicit definition definitely has some advantages. It basically is where we give a rule. It's very convenient in that we have a rule that defines each individual term of the sequence based on which term it is. So for instance, I have a rule that will tell me what the 100th term of the sequence is, or what the 10th term is, or what the 13th term is. So it's very nice for determining individual terms. So what this is, you can write that down, is each term is defined by a rule that is based on knowing the number of that term. In other words, is it the 99th term, the 100th term, the 101st term, whatever the case may be. The other way that we can define, let's look at an example of that first. So here is a rule that defines, it's an explicit definition. So it's our sequence, our terms in our sequence, those are our a sub n there. They're equal to n squared minus 1. So if I want to know the 100th term, I put 100 in for n, square it, and subtract 1. So I know it would be 9,999. That's simple to find each one. So the way that we would notationally talk about this is this a sub n refers to the entire sequence. And generally, we index this n starting at 1, so this indicates this sequence starting at A1, A2, A3, A4, and etc. So if I'm looking at this sequence here, this definition would give me, if I put 1 into this, I get 1 squared minus 1, so the first term is 0. The second term would be 4 minus 1, so it would be 3. Then when I put a 3 in here, I would get to 8. When I put a 4 into here, I would get the 15, and so forth. It keeps going up like that. In this case, if n is the natural numbers, this is an infinite sequence. But like I said, if The nice thing about this is I can build it individually, but if I want to know the 100th term, I can find that right away. So here, if I want the 20th term, I know it's 399. Simply put in 20 here, square it, get 400 minus 1. If I want the 9th term, it's pretty easy to do that, get 80. That's the advantage to that method. All right, here's another example where we've got a sequence. We'll call this one B, and the terms B sub n are defined as 2 over n plus 1/2. So here we find that the sequence is going to be, if I put in n of 1, I would get 2 plus 1/2, so I'd get 5 halves. If I put in n of 2, I would get 1 plus 1/2, I would get 3 halves. If I put in an n of 3, I would get 2/3 plus 1/2, which is going to be 7 over 6. Put in a 4, I'd get 1/2 plus 1/2, I get to 1. And this is good. Pattern is going to continue as it goes on. Interestingly enough, as this sequence goes on, the values here will get closer and closer and closer to 1/2. And we can talk about why that is later. All right, the other way to define a sequence is with a recursive definition. The advantage to the recursive definition is a lot of times it's much easier to figure out. Sometimes it's difficult to figure out what the rule is. Like, for instance, if you look back here, if I just gave you this sequence here, it might be difficult to figure out that that's the rule. If I gave you this sequence right here, it probably would be rather challenging to figure out that this was the rule. So there can be, the recursive is usually easier to figure out a rule. The other advantage to recursive is there are some sequences that do not define well explicitly, but can define very well recursively. So what is a recursive definition? That's where each term is defined using one or more of the previous terms. So in order to know what say the 100th term is, we need to know what the 99th is, and then we can say what the 100th is, or we need to know maybe the 98th and the 99th, something like that. We need to know just the terms that come right before it. We define each term based on the previous term. The disadvantage to this is if you want to know the 100th term, you have to know the 99th term. And unfortunately, a lot of times that means you have to know the 98th. So it means you have to build the whole sequence in order to know certain terms. So when doing a recursive definition, the steps are you must first define the beginning term or terms if you're defining the next term based on more than one term. Then you define the rule for the succeeding terms, for the rule that gives you the next terms as they come up. So let's look at an example of how we do this. So here is a sequence, and we'll do this a couple ways. We'll start with doing it where we start with the rule and then generate the sequence. We'll also look at the sequence and generate the rule. So we know our first term is -3. And here's the way we define our rule. Our rule says that, for instance, if I want the nth term, I have to look at the previous one, the n-1 term, and add 2 to it. So for instance, if I want, say, the 10th term, I need to look at the 9th term and add 2. So in this case, I know the first term. If I want to know the second term, so if I'm going to go list these, so the first term is -3. If I want to know the second term, I have to look at the 2 minus 1, or the first term, which is -3, and add 2 to it. So that would be -1. Then if I want to know the next one, if I want to know the third term, I would look at the second term and add 2 to it. So I would get -1 plus 2, and I get 1. So essentially what I'm doing is I'm adding 2 to the previous term every time. And so we can see that we have this sequence right here. Let's look at another example. This is a very famous sequence here. And this is one that's, to my knowledge, you really can't define it explicitly. You have to define it recursively. So we're going to let the first term be 1, the second term be 1, And then we're going to define the nth term to be the sum of the previous two terms. So the a minus 1 is the term right before the nth term, and the a minus 2 is the one that's 2 before that. So let's look at how we generate this. So our first term is 1, our second term is 1. Our third term is going to be the sum of the previous two terms. That's this here. So the third term would be the sum of 3, the first term, and the second term. So the first and the second, we add the 1 and 1 together, and we get 2. So the next term, the fourth term, I would have to add the second and third together, so I would get 3. For the next term, I would add the 2 and the 3 and get 5. You can see how this is going, 8, 13. And this actually is a very famous sequence. Pause now to see if anyone knows what it is. Well, I don't know if anyone gave an answer. I just can't know on video. But it is the Fibonacci sequence. So gold star if you happen to know that. And it's famous. It occurs in nature a lot of time, in a lot of situations. It occurs like in seed patterns in strawberries and sunflowers and other things. So it is one of those things that we see coming up in nature quite a bit. All right, the other thing we need to be able to look at and understand are the limits of sequences. So for instance, it's pretty easy to see that as I go along here, there's no limit to this. Okay, it's going to keep growing. Same thing with something like this. But if you remember, as I looked back on this, here, now these terms are getting closer and closer to a particular value. And it does happen to be 1/2 in that situation. So let's take a look at how we figure out the limits of sequences. Well, the first thing, we need some terminology. So if it does approach a particular value, we say that it converges. So that means that the sequence does have a limit. So for instance, this one here would not have a limit. We would say it diverges. The one up there for the b sub n, we would say that converges. And diverges is the term that we use to say that the sequence does not have a limit. So in today's homework, I really believe it's going to be pretty straightforward. It's mostly going to be genuating terms of sequences and saying whether things converge or diverge, but not actually figuring out what they converge to or what they, obviously, if they don't diverge to something. So I think that as far as the homework goes there, you won't have to worry about figuring out what the limits are. We'll talk about that with our next lesson. But if you do have to find out what they go to, something like this, what you have to do is you have to look at the explicit. One thing to do is plot enough of them so you can figure out, I mean, obviously what's happening is these keep getting less and less and less and less each time. But the question is, okay, they're getting less and less. Are they going to 0? And if you go out far enough, you'll see, no, they're actually not going to 0. If you look at the general definition, we can see here, as n goes to infinity, this thing here goes to 0. So it gets closer and closer to 0 plus 1/2. So it gets closer and closer to just being 1/2. But it's always going to be bigger than 1/2 because this is never going to actually be 0. It just gets closer and closer and closer to 0. So like if n was 1 million, you'd get 2 over 1 million. 1 over 500,000. That's very small, getting close to 0, but it's not 0 yet. 2 over 1 billion, it's still not 0, although it's even closer to 0 than 2 over 1 million was. And that same kind of thing happens as n gets bigger and bigger and bigger. Okay, with that, your homework is going to be 9.3, do 1 through 20. So 9.3, 1 through 20, and start getting familiar with working with these sequences. I think this should go pretty quickly. But it is important that you understand how to work with this notation and what's happening with these sequences. Okay, look forward to seeing you tomorrow.